a little bit, I guess, before I introduce our first speaker, about like the origins of like this research cluster and this seminar and what we wanted to do. Essentially, it's born out of the idea that quite a considerable amount of, air quotes, serious maths comes out of recreational maths or hobbyist maths, things like puzzles, things like, you know, the old Königsberg bridges, things creating graph theory as we know it. And this is true both of contemporary maths and historically, going back, you know, all the way to the Babylonians and the Egyptians. And one of the really nice things about recreational maths, the definition of which is something Peter's going to talk about in his talk, so I'm not going to say much about what we mean by recreational maths just yet. One of the nice things is it tends to draw upon lots of different areas of maths. It has lots of interplay with things like the history of maths, and it's useful in maths education and public communication of maths. So it's got this sort of very broad appeal, and kind of what we're looking to try and do is to sort of provide a common, for now, virtual place to draw together people with interests from all these different areas, and sort of recreational maths broadly interpreted. So we're really trying to sort of be as broad as possible with what we're thinking of as recreational maths. Okay, so with that out of the way, I'll introduce our first speaker. So our first speaker is James Grime. He obtained his PhD from the University of York and lists his academic interests as, amongst other things, it's quite a list, group theory and combinatorics. He later joined the Millennium Mathematics Project from the University of Cambridge, where he was until about 2014. He now, I think he still runs the Enigma project and travels across the country and beyond, sort of giving public talks. And he's also a professional YouTuber with both his own channel and a regular presenter on the Numberphile channel. Today he's going to talk to us about Go First Dice for 5 players and beyond. So, James.
Okay, I guess over to me. Yeah, so just to say hi to everyone. I hope I'm unmuted and everything's working technically. I've got thumbs up coming from people. That's nice to see. So let me introduce myself quickly. So yeah, I'm James, and I do, like I was introduced, I travel around, I give talks, and I make these YouTube videos about maths. And I guess what I do is maths as entertainment. So what I have to do is find curious mathematical facts, quirky mathematical facts, and present it as a kind of entertainment. Or you're presenting mathematics as maybe a game or a magic trick, or maybe as a toy. And that's kind of what I want to talk about today. So this is going to be mathematics as a toy. It's a problem I've been working on and off for quite a few years now. And it's a dice game or a dice problem. So I'm going to share my screen and we'll have a look at this. So it's called Go First Dice. So let me set up the problem then. So imagine you've got 4 friends, right? Imagine that. So you've got 4 friends. So let's see if we can get this up. Here we go. Here are my 4 friends. And let's say my 4 friends here want to play a game. So they need to decide who goes first, second, third, and fourth. So to decide, they decide to roll dice. So they're going to roll dice and then they can order play from highest to lowest. The problem with that, though, is that 2 players might roll the same number. And then if they roll the same number, they're going to have to roll again. And maybe they'll get the same number again and they'll have to roll again. And potentially this could go on forever. So the question is there a set of dice that we could design so that we would have no ties, so that we could have 4 players and each player is equally likely to be first, second, third, or fourth? So the solution of this problem was found in 2012. It was found by Robert Ford and Eric Harshbarger, and it's this set of 4 12-sided dice. I actually have them here. It's a real thing, right? So it's 4 12-sided dice. So if my 4 players use these dice, they can roll them, and they'll be equally likely to be first, second, third, or fourth. But what's even nicer about these dice is that if 3 players decide to play a game and they roll dice, they will be equally likely to be first, second, and third. And in fact, that's true for any subset of 3 players. So any subset of 3 players, if they roll these dice, they'll be equally likely to be first, second, and third. And the same is true for subsets of 2 players. So if they roll the dice, they'll be equally likely to be first and second. And like I said, that's true for all possible subsets. So that's kind of nice. That's kind of neat. Nice little dice toy. So the obvious question then is, what about 5 players? So I learned about this problem in 2012 from the Alex Bellos blog, the Guardian blog. And in that article, he describes the problem. So we're looking for a set of 5 dice now, such that there are no ties, each place is equally likely, and this will work for all subsets of players as well. So this is the problem that I decided to take on. I actually did this with a friend of mine, Brian Pollock, and together we designed a set of 5 Go First dice, and this is what they look like. So it's this, it's a set of 5 60-sided dice, but this will work. So if you roll these dice, you'll be equally likely to be first, second, third, fourth, and fifth, and that's true for all subsets as well. So what I'm going to do is spend about 20 minutes, and I'm going to tell you about the maths of this, how we've designed this set of dice and how we got there. Then that will be about the halfway mark. And then at the halfway mark might be a good time for a pause. And if you've got any questions about what I've done so far, that might be a good time for that. So I think we're putting questions in the chat, and then we can get some questions at the halfway point. And then I want to show you a second solution to this problem. So this is a second set of 5 Go First dice, which look like this. This is called the inductive construction. And this is a particularly weird set of looking dice. They're all different sizes. So I want to talk about this set as well, how this was found, and the differences between these 2 sets. So there's kind of pros and cons for these 2 sets. Now, I am going to get into the maths of this. So I said at the beginning that I guess my job is to do maths as entertainment. And I am making no promises to be entertaining today, right? So I'm going to go into the maths of this and how they were designed. It's undergraduate level maths, but if you're not into dice, that might bore you. And I apologize for that in advance. I find that the binary construction, which is my first set, that's a little bit harder conceptually. If I do baffle you, and I do apologize, don't worry too much. Come back for the inductive construction, which you might be able to follow instead. Okay, so let's get into my first set of 5 Go First dice. So this was the binary construction. So what we wanted to do, and that was me and Brian, we wanted to do a computer search, but a computer search was going to be large. So we will have to search through all possibilities of 5 dice. And we knew that was going to be large because we knew already that the number of sides had to be divisible by 30. So why did we know the sides were divisible by 30? So let me show you. So if we've got 5 m-sided dice, so that's our setup. We've got 5 m-sided dice. Then the number of outcomes is going to be m to the power 5. Now we want each place to be equally likely. For example, I want each player to be first 1/5 of the time, which means that m to the power 5 must be divisible by 5. However, because 5 is a prime, if m to the 5 is divisible by 5, then m is divisible by 5. So we know that, but also we want this to work with subsets. So if I had a subset of 2 dice or a subset of 3 dice, I want those places to be equally likely as well, which means by the same argument, m is divisible by 2 and 3. So you put that together and we know that m is divisible by 30. So we might be looking for 5 30-sided dice. So it's going to be a huge problem, even by computer search. So we wanted to restrict our search a little bit to sets of dice that were particularly nice. So particularly nice dice for us to find. So this is going to be our binary construction. So I'll show you an example of a binary construction. So here is a set of 3 6-sided dice. As you can see, I've written the dice in rows. So those are the values of each die. So I've got my 3 6-sided dice. Now, a couple of things I want to point out about this. First of all, look at the columns. So the columns are filled sequentially, by which I mean in the first column, we have 1, 2, and 3 in some order. Then we have 4, 5, and 6 in the next column. Then we have 7, 8, and 9, then 10, 11, 12, 13, 14, 15, and 16, 17, and 18 in some order. So the columns are filled sequentially. The other way to make these dice nice is that the last die contains the highest and the lowest value of each column. Now let me show you that. So if you look at die C there at the end, and these values, the 6, the 9, the 15, are the highest in their column. So 6 is the highest in its column. You can see that. 9 is the highest in its column. 15 is the highest in its column. And 1, 10, and 16 are the lowest in their column. Hopefully you can see that as well. So that was the highest and the lowest values in their columns. Now I'd say the last die there, but actually we're going to build these dice up one at a time. So actually this would start with A, then we'll look at B, and that would be the same. So we start with A, then we build up B so that we have high and low values. So in this case, 3, 8, and 18 are higher than A in that column. 4, 11, 13 are lower than A in that column. And then C was the same idea. To really emphasize this idea of high and lows, what I can actually do is rewrite these dice so that each dice has 2 values, a high value and a low value, which is a value that is higher than the previous dice and a value that is lower than the previous dice. Now, if you look at that here, first of all, you might notice that the first die, A, is essentially a dummy die. This is all to make the wins easier to count. So look at A. So that's a dummy die. That's not really doing anything. That just has the same value all the way across. Then we add in B. And the idea here then is we have half the values are higher than A, half the values are lower than A, which means B wins half the time, loses half the time. That's what we want. In the same way, C has half the values are higher, half the values are lower. So in a 2-player game, it would win half the time, lose half the time. And that's also true in a 2-player game with B. So half those values are higher, half those values are lower. So you're equally likely to be placed first and second. That's in a 2-player game. Now in a 3-player game, it gets a little trickier. So in a 3-player game, the position of those high values matter. So what we're going to do next is work out where to place those high values. So we're looking for the position of those high values. So let's look at the original set again. So that was the sets that we already had before. And let's say player C rolls the die and he rolls a 9, okay, which means that he's rolled side 3 there. That means that he will automatically beat any value or any outcome which is lower. So that means he automatically beats these outcomes in the yellow box here. So if A or B rolls any of those outcomes, it doesn't matter what the values are. If he rolls those outcomes, then player C will automatically win. And that's because of the way we numbered the columns sequentially. So that's an automatic win for C. Now, I'll do an example here then. So we've got an example of 6-sided dice, M equals 6. So altogether, there are 216 possible outcomes, so 6 cubed, and each die automatically is going to win 55 outcomes, right, without even thinking about what the values are. So each die automatically wins 55 outcomes. That means there are 51 outcomes left to think about. So there are 51 outcomes left. We want player C to win 1/3 of those outcomes, and that will depend on whether C has a high value or low value. So in fact, if we label our columns from 1 to M, I've got 1 to 6 here. So if you label your columns like this, then a high value on side S will increase the number of wins by 2s minus 1. I'll show you what I mean. So at the moment here, C has rolled the third side, and he automatically wins 4 outcomes. So if A and B have rolled lower sides. If the value on side 3 is high, it is high in this example. So if that's a high value, then you will increase your number of wins from 4 to 9, which means player A and player B are rolling these outcomes in the yellow box here. So those outcomes, those wins, have increased from 4 to 5. Now, in general, if we had m-sided dice, so 3 m-sided dice, you would have m-cubed outcomes. So you've got n-cubed outcomes. Your automatic wins is this little formula here. It's a sum of squares, and then you multiply it by 3 for each player. So that's your automatic wins. Then we will subtract that, so you get those contended wins, and we need C to win 1/3 of the remaining outcomes. So you get a little equation like this. So you've got the total number of outcomes is n cubed, subtract the automatic wins, C needs to win 1/3 of those, and you get a little magic number here. Here's a magic number. It's m times 3m minus 1 over 6. Okay, that's going to be our magic number. So if you have a high value on side S, that increases your wins for up to by 2s minus 1. So those wins have to add up to our magic number, which is what I just showed you. So you get this little formula. So if you solve that little formula, that will tell you where to place the high values on die C. So let's do this in our example. So in this example, our high values were on side 2, 3, and 5. And now that needs to add up. Each one contributes 2s minus 1. So each of those high sides are going to contribute, if I do them in turn, 3, 5, and 9. And that adds up to our magic number. Our magic number was 17 in this example, which is exactly what I wanted. So these high sides add up to 17. So that little formula is telling you where to place the high sides. But I can make that a little bit neater, because I also know that half the values on C are high values. So using that, if I send that summation sign through that little equation there, break it up a bit, so it looks like that, that second summation sign I can replace, because I know that that summation sign is going to be equal to m over 2. And that's because half the high sides, or half the sides, are high. And then you can rearrange that little formula. So you get an equation where you're saying that the sum of the high sides is equal to this magic number, a different magic number now. So in our example, we had m equals 6. And in this case, the magic number would be equal to 10. And if you look at our example, our high sides were 2, 3, and 5. And that does add up to the magic number 10, which is exactly what you want. So that's a condition that you need to satisfy for your dice to be go first fair. So we've got this nice little condition. What about for more than 3 players? That was 3 players. What about 4 or 5 players? So we can do this in general. Okay, so if I have a high value on side S of the kth dice, it increases your wins by this amount. Previously, it increased your wins by a difference of squares. It was a difference of squares before, and now in general, it's going to be a difference of k minus 1 powers. So you get an increase of wins by this amount. Now your kth die must win 1k of these contended outcomes. You've got the total number of outcomes minus automatic outcomes, and we need to win 1k of the remaining outcomes. So you get, oh, and I should add this as well, your kth die must satisfy all the conditions for sets of k dice and fewer. Like my example before, with 3 dice, The third one had a condition, but it also had a condition that it had to satisfy for subsets of 2. So it's doing those 2 things simultaneously. So that's what we've got in general. All right, so that's a whole bunch of setup. Put all that together and you're going to get a set of conditions. So I'm just going to tell you what these conditions are. So if you define your dice by their high sides, let's just call those SI. So that's a list of their high sides. Then we've got some conditions. The first one is a condition for the first die. And well, the first die is a dummy die. There's no maths involved in this. So the first die is a nothing die. So I'm just going to say first die is M-sided, fine. For your second die, we have a condition, which was half the values have to be high. And that's what I've written here. For the third die, that's true, plus an extra condition, which we just worked out. For your third die, the sum of the high sides had to equal this magic number. There it is. And now, if we do a fourth die, it would have to satisfy what we've done already, and it would have an extra condition for the fourth die. And the extra condition is a condition on the sum of the squares of the high sides. And you get another magic number for the sum of the squares of the high sides. For your fifth die, it's all the above and a condition on the sum of the cubes of the high side. So you get these nice little set of equations here. If you satisfy this, we should be able to find our set of 5 go first dice. But I'll do an example first. I'll do an example of 4. So here's an example of 4 go first dice. Kind of the idea we saw before. You've got your dummy die at the top, and then you've got high and low values like that. So this is our set of 4 go first dice. And this does satisfy the conditions I've been talking about. So if we look at die B, here are the high sides. And when it only has one condition to satisfy, half the values need to be high values, which is true in this case. For die C, these are the high sides. There you go, I've just listed them out. And that has 2 conditions to satisfy. Half the values are high, that's true. And if you sum up the high sides, you get a magic number, which is 38 in this example. And for your fourth die, same thing. You've got a list of high sides, and then you have 3 conditions to satisfy, which is half of them are high, we've got a magic number to add up to, and the squares of the high sides add up to this other magic number as well. So this set of dice satisfies all those conditions. I will say that these are necessary conditions, not sufficient conditions. Now, I'll add one other thing to this, kind of neat, a whole bunch of little summation conditions, and they kind of end up being rather compact and neat. But I'll add one other thing to this. Now, I'll just point out by observation so far that have a look at these 2 dice here, C and D. Have a look at the columns where we have high and high values. So there are 2 columns where high and high values appear. In fact, there are 2 columns where you have low and low values. There are 4 columns with a high and a low value, and 4 columns with a low and a high value. And this observation is true in general. So there are actually conditions that we can put on the columns of the dice. Now, I'm going to show you how to justify this and where this came from in 60 seconds, because I think at this point, if I went into the details of this, this would be one too many things that I'm talking about. So in 60 seconds, I'll just tell you how to justify this. Let's have a look at it. So these are column conditions. And the point is this. I said before that you had contended outcomes that were not automatic. And then C, die C, had to win 1/3 of those contended outcomes. That means die C loses 2/3 of those outcomes. And that means for everything to be equally likely, then die B needs to win half of the outcomes not won by C. And that's kind of the justification of this. So the second die must win half the contended outcomes not already won by the third die. So we're looking at columns where the second die has a high value and the third die has a low value. So that's what you're looking at. And then, well, if you add in a little bit of maths here, in fact, if they both satisfy condition 3 from my slide, which had a whole bunch of conditions, you can deduce something. You can deduce that the high, low values appear in 1/3 of the columns. And then it's an easy consequence once you've got that of all the other things that I told you. The high and high values occur in 1/6 of the columns and all the rest of the things that I told you. So you have these column conditions as well. And that is satisfied by this set of 4. And so, in fact, if you now look at this complete set, we can now relabel these sets by labeling each column with proper numbers, right? So I'm going to fill these columns in now with the numbers sequentially, like I did at the beginning. So in the first column, 1, 2, 3, 4, 5, 6, 7, 8, and the rest. But I do that so that I preserve the order that I've got there. So the order of the columns are preserved. If you do that, you'll get this set of 4 dice. There they are. There they are with proper numbers. But it turns out that this set of 4 dice that we found is the original set of Go First dice, the original set of 4 12-sided dice. The original set was not built in this way, but it turned out that the maths that we were working out turned up the original set. So it was included in the maths that we were doing as well. So that's kind of nice. So now we can move on to answer the proper question, which was, can we find a set of 5 dice for 5 players? So this was going to be a computer search, still a large computer search, but now we've got some necessary conditions. So some conditions to satisfy means we can eliminate the wrong answers. That's the important part of it. Now, in fact, even before a computer search, you can actually work out that when you have m equals 30, which is 30-sided dice, there are no solutions. There are no die, or there is no die, that would satisfy all those conditions. So you could use it as a 5th die. So it can't be done. You can't do it with m equals 30. So you had to move on to m equals 60. So we continued our search looking for 60-sided dice. Now, it's still a large search. So there were a couple of hunches that we were using here. First, a hunch was we made the 4th and the 5th die interchangeable. So they don't have to be interchangeable. The 5th die has one extra condition that it has to satisfy than the 4th. But we said, let's make our life a bit easier. So the 4th and 5th are actually completely interchangeable in our maths. And again, this is just by observation, just hunches. Another hunch was to make the 5th die a bit inverse palindrome. What that means is, if you took the high and low values for the 5th die, if I reverse the order and then swap highs and lows over, then I get the same die back again. Now, the reason we did this is completely by observation, things that we've noticed, and it was actually my partner in this, which was Brian, who noticed this, and I believe he's right, but it's stuff that just hunches that we've noticed. And finally, what we were doing is we were building our sets backwards from the 5th die. So you started with the 5th die, looking for dice that satisfied all those conditions, and then built the 4th die backwards from there, which would then satisfy column conditions and whatever, and built backwards from there. Also, I'll just throw this in, we did find some other conditions, particularly for B. I won't go into that, that's way too much to talk about. So there were some other conditions that we threw into that. And using that computer search, yes, we finally found an answer. And this was the answer that we found. So it was these 5 60-sided dice using numbers 1 to 300. And look, here they are, actually printed out. So 3D printed 5 Go First Dice. There they are. And we were so excited. We were so excited about this. So pleased with ourselves that we had solved the problem. So we went to the originator of the problem, which was Eric Harshbarger, who invented the original set of 4 dice. And we went to him all kind of pleased about it, going, oh, look, Eric, we found a set of 5 Go First dice. And Eric's reply, to my memory, was, great. Is each place equally likely or each order equally likely? And I said, isn't that the same thing? And Eric said, no, it's not. So it's not the same thing. And he's absolutely right. So this was our set of 5 dice. And A, let's say die A and die E, they're both equally likely to be first. They're both equally likely to be second and third and so on. However, the order A, B, C, D, E is not as likely as E, D, C, B, A. So the place values were equally likely, but the orders were not equally likely. So it turned out that there is more than one definition of fairness. So we actually used 3 definitions of fairness. The first definition we call Go First Fair, which means you're just interested in having each die being equally likely to be first. And that's called Go First Fairness. Place Fair is where each place is equally likely. And that's kind of what I was working on. And then there's Permutation Fair, where each order is equally likely. And for these dice, what we were interested in was that was true for subsets as well. So we have these 3 definitions of fairness. So what I've done is we had all these conditions, which were necessary conditions, that are actually necessary for Go First Fairness. That's the actual thinking I was doing. I was saying, you know, I want them to be equally likely to win. So that meant they were equally likely to be first. So that was the maths that I was doing. And then that allowed me to reject incorrect solutions. So you can't be place fair if you're not Go First Fair. So I can reject the incorrect solutions, but then we would need to do an additional check for place fairness, which is what we did. Then we said, oh, and this set also works for place fairness. And you would need to do an additional check for permutation fairness. But that was not the problem I was working on. And to be honest, I was pretty annoyed about this because I felt like the goalposts had been moved on me. So I had been solving the place fairness problem. And then it turns out Eric had moved on and he was far more interested in permutation fairness. I was a little bit annoyed. And so I kind of left the problem for a while until we all came back to the problem when we found a new set of dice, which was going to be permutation fair as well. But I did say that I would break it into 2 halves. So that's the first half of my story. And I'll do a 1 minute, 2 minute break here. And I'll ask if we've got any questions so far. Do we have any questions so far?
So, Katie, do we have anything?
I've not. I'm unmuted. I've not seen anything come up in the chat.
Cool.
I guess, I mean, I had a vague question that had occurred to me, which may be relevant to the whole thing, but are you planning to publish this, or have you already published this as a paper anywhere?
Right. So this is a good time to mention this. So I've written this up, and I've written it up as a paper, and including what I'm going to do next. And I'm struggling to find a place to publish it because it's all about tone, I guess. Because if I want to publish it in a place where they're doing recreational maths as entertainment, then this is just not entertaining enough because I want to go into the details. I put work into this and I want this to be recorded somewhere. And so somewhere that wants to do it for entertainment are not going to be interested in this level of detail. And if I want to publish it somewhere more serious, the problem is perhaps a little bit trivial, a little bit recreational maths. So I'm finding that difficult place to publish it in that kind of point of view. So I'm actually interested in someone to have a look at this paper that I'm trying to write. I've got different versions of it, also sort of different levels. And sort of edit me, try and find a place where we could publish it, and maybe where I can get as many details in as possible, but a place that would find this problem interesting. Does that all make sense?
Yeah, I mean, I'm sure there must be recreational maths journals, and I suspect if any group of people is going to know about them, it'll be the people who are watching at the minute. So if anyone does know of any good recreational maths journals that might be interested in publishing this kind of thing, please feel free to pop the details in the chat. I think if you're happy to do one more question before you move on to...
Yeah, there is a question.
So there has a couple of questions that have come in, one of which actually occurred to me earlier on. So at the start, you were saying that it needs to be divisible by 5, and then if you also want it to work for smaller sets as well, it would need to be divisible by 2 and 3. Would you not also need 4?
So the maths that I was used prime numbers. So the number of outcomes is divisible by such a number, and if that number is prime, then the number of sides is divisible by that prime as well. So it's the primes that I was interested in, the 2, 3, and the 5. Okay. And the 4 wouldn't help me.
It's turned out that you needed 60 anyway, which is also
yeah, and maybe someone can justify why it needs to be divisible by 4 as well then.
Potentially. Okay, so I think there's been a couple of comments with suggestions for recreational maths journals, which we can pass on to you after.
Yeah.
I think there's been a question about possible applications for this, if you want to address that at the end or now, or...
Well, as for applications, I haven't thought of any. This is purely a pure maths thing, a purely kind of recreational maths thing. I haven't thought of serious applications for this. No, I haven't. The recreational journals, great. I do know a few of them, and I probably know some that you've mentioned. I think I need some advice so that I can be successfully apply this to those journals. So if someone is an editor or someone like that, they can help me out. Now, if I'm all still screen sharing, I might as well crash on to my second half. So if I have baffled you there with that first 20 minutes, totally fine. I do think that's actually conceptually tricky. So maybe you'll enjoy the inductive construction. So I'll show you how this works. So this construction, we came up with a couple of years later, and I'll give you an example. Okay, I'm going to start with this set of dice here. First of all, they're different sizes. So die A, 2-sided dice, B is 4-sided, C is 6-sided dice. So we've got these different sided dice, and altogether there will be 48 possible outcomes. And I'm telling you that in this example here, each order of A, B, and C is equally likely. So every order is going to appear 1/6 of the time. So I'm going to tell you that this set is permutation fair. What we're going to do next is, starting with a set that is permutation fair, we can add on an additional die and keep the set permutation fair. So that's what we're going to do. So if we've got a set, we can construct a set of n+1 permutation fair dice, starting with a known set of n permutation fair dice. So that's what we're doing. Okay, now this, to give credit, this idea first turned up by some guy called Paul Venetti on a blog post, and I think he did like a set of 4 Go First Dice, and there was no details. It was just, look, here's a solution for 4 Go First Dice, here they are. And no details were given. And so we never found out how he got there. So in fact, Robert Ford and Eric Harshbarger, who were the original people who solved this problem, the set of 4, kind of reverse engineered the construction. So they reverse engineered it, and then they started to look more deeply into it. Eric proved that this construction that they've found does work and does make Go First Fair dice. He conjectured that this construction would also be permutation fair. It seemed to be true, but he hadn't proved that to be true. And then last year, I kind of sort of tidied up that proof. So I can confirm that these sets are permutation fair. So let's take a look at what this construction looks like. So you're starting with a set that is permutation fair, and a little bit about notation here. So this is my 2-row notation. Hopefully you can see the idea of it. What I'm doing is labeling where each value appears, on which die each value appears. So 1 appears on die C, 2 appears on die B, 3 appears on A, 4 appears on B, and that's my 2-line notation for that. Of course, I could write this more simply as a 1-line notation. So those letters will tell me which values go on which die. So that's my 1-line notation for this. Now, what we're going to do is something called an expanded set. I'll show you what that means. So we start with our original set. That's the set I had before, just in a smaller font. So that is the original set we were starting with. What I'm going to do is I'm going to make 3 copies of each of those values. So I'm going to make 3 copies. I'll show you what I mean. It looks a little bit like this now. In fact, that's still a bit small. Let me zoom in on that. There you go. So this is called an expanded set. What I've got for die A, it had 3 and 10. The values were 3 and 10. And I've just repeated that, 310, 310, 310. So I've made 3 copies of those values. And then to distinguish between the 3 copies, you can see I've added 100 onto the first copy, I've added 200 onto the second copy, and I've added 300 onto the third copy. So you can tell which copy is which. And so these are our expanded dice. And to distinguish them from the original set was called A, B, and C. And the expanded set, I hope you've noticed, is Comic Sans A, B, and C. And here's my claim. If the original set is permutation fair, the expanded set is permutation fair. That might sound natural and obvious, but I'm going to try and prove that that is true. So if the original set is permutation fair, the expanded set is permutation fair. So, for example, if my original set, if the probability that A greater than B greater than C is 1/6, so if that order, A, B, and C, is all equally likely, so it should be 1/6, then I claim that that will be true for Comic Sans A, B, and C as well, the expanded set. So let's prove that's true. So let's say we've got A greater than B greater than C. That means A, B, and C can land on these copies. So here is a list of sequences where they're allowed to land. So A, B, and C could land on 333, or they could land on 322 or 211. If they don't land in that order, then you're not going to have A greater than B greater than C. So that's a list of weakly decreasing sequences. So that's where A, B, and C land. Now, we want to work out, or I'll just say this, if you land on the same copy, 333, 222, 111, if your dice land in the same copy, you're automatically permutation fair. You'll get that inherited from the original set. If your dice land on some sort of split, so in this example, some of them, 2 of the dice have landed in the same copy, 1 of them landed somewhere else, then the subset of 2 that land in the same copy are permutation fair. You get that from the original set. Or they might land on distinct copies. If they land in distinct copies, we already know A greater than B greater than C, because it has to be. So now, and the probability of each sequence, well, they're all equally likely. It's 1/3 cubed. Okay, I'm interested in this probability. A greater than B greater than C. So we just put in the figures that we've got now. Each sequence is equally likely. It's 1/3 cubed. If we look at the sequences where they all land in the same copy, probability A greater than B greater than C is 1/3 factorial, or 1/6, because that is inherited from permutation fairness. If you look at the sequences where you have a split, and this is a 2-1 split, then the probability in this example would be 1/2 factorial, 1 factorial. So that 2 factorial is coming from permutation fairness of 2 dice. And then finally, our other example was the die lie in different copies, and then automatically the probability that you've got A greater than B greater than C is 1, because that has to be true. Or if you prefer, we could write that as 1 factorial, 1 factorial, 1 factorial. There's a little sum to do. Do that little sum. The answer is 1/6, which is what I wanted it to be. So that is true. So that is true, and it's true in general. So that was just an example, but that is true in general as well. So if you've got n dice, let's call them x1, x2, up to xn, I'm going to make r copies. Now that's a choice. How many copies I make is a choice. So I could make 1 copy, or 2, or 3, or 10, or 500 copies. So I'm going to make r copies. The probability of each sequence, do you remember those weakly decreasing sequences? They're all equally likely. It's going to be 1 over r to the n. And then if we've got this split where you, let's call it ni dice occupy the ith copy. So that's where the dice are kind of split up into fitting into different copies. The probability of this ordering, x1 greater than x2 and all the rest, is that little product of factorials. That little thing that I've done there is exactly the same thing I did in my example. So you get that little product of factorials. Putting all this together, if you sum over all sequences, you get this value. It's r to the n over n factorial. Now, I'm going to cite that as a fact. And my citation is the online encyclopedia of integer sequences. If you've got a better citation for that fact, I'd like to hear it. I would prefer that. So if we take that as a fact, then finally putting it all together, because each sequence is 1 over r to the n, that probability, which I'm interested in, is 1 over n factorial, which is exactly what I want. That's exactly what I needed. So and that's true for all the orders. So I did an example here in the regular order, x1 greater than x2 greater than x3, but that argument works for any sequence that I want, and it would also work for subsets of dice too. So I conclude, what I'm going to say is that yes, expanded sets inherit the permutation fairness. So a bit of work there, but yes, that is true. Okay, expanded sets inherit permutation fairness. So I'm not going to distinguish between the expanded set, which was my Comic Sans, and the original A, B, and C. So I'm just going to call them A, B, and C now. So those are my expanded dice. Now we're going to construct a new die, a 4th dice. We'll call it D, and D will have values that are going to fit in the gaps. So it's going to have values that are going to be less than 100, and then values that fit in the gap between the first copy and the second copy, and then values that fit in the gaps between the second copy and the third copy, and values greater than the third copy. So that's where we're going to place our values for our new dice. And in one row notation, it would look like this. So that red, blue, and brown, that is my 3 copies that I made. And this D0, D1, D2, D3 are going to be placeholders for where I insert values for dice D. So that's what we've got so far. I want to work out how many values we need to insert in those positions and keep the set permutation fair. That's the problem. Okay, so to solve that problem, what I'm going to do, there's my 1 row notation again. Let ki denote the number of values at di. If you get the idea, so k0 and k1, k2 and k3. Then D, the dice D, will have the sum of ki faces. We'll call that capital K. That's how many faces D will have. I'm going to find those values of ki by calculating the probability of some orders. So here's some orders that I'm going to calculate. So let's do a calculation. So it's a probability calculation. Let's work out the probability of A, B, C, D. And to work that out, I split up the problem into 3 parts. So here is the problem, and I'm splitting it up. Let me break this down. So in the first part, I'm looking at the probability that D lands in one of these placeholders. So the probability that my die lands in placeholder D0, there are K0 values there out of K faces. So that's the probability you would land in the first placeholder. Probability you would land in the next placeholder would be K1 over K. And for the next placeholder is K2 over K. And the probability you land in the last placeholder is K3 over K. The next step, what's the probability that A, B, and C are greater than D? Because that's what I'm interested in here. So probability that A, B, and C land in a copy that is higher than your place value. So if we work that out, if you land in D0, your 3 dice, your A, B, and C, are definitely going to have higher values. So that's a 1. And for the second placeholder, D1, the probability is going to be 2/3 because there's 2 copies that are higher than D1. 2/3, that's for each of the 3 dice. So it's 2/3 cubed. In the same kind of way, if you land in D2, your probability of being higher is 1/3 cubed. And for your last placeholder, you can't have higher values. So that would be a 0. And then our third step of this is working out the probability that A is greater than B, greater than C. But that is inherited from permutation fairness, even in this expanded set. That's going to be equally likely for all orders. So that probability is 1/6, and I can put that in my little equation. So I get that little calculation to make. So I'm going to do that calculation, but I'm going to do that kind of calculation for these different orderings. So I've got 4 different orderings that I care about. Can you see I'm just kind of moving the letter D through that order? So D's in the last place, in the third place, in the second place, in the first place. I'm going to do that calculation again for each one of those. It looks like that. Do the calculation. I'll show you what that calculation looks like. Bit ugly, there it is, that's the whole thing. But here's what I know. If I want my set of dice to be permutation fair, these probabilities have to be equally likely. They have to be set to 1/24 or 1/4 factorial. So I set those probabilities to be 1/24, and then I solve. So you solve that little system of equations, and you can get the values of the Ki. And in this example, here they are. Right? K0 is 1, K1 is 3, K2 is 3, K3 is a 1, and altogether you've made an 8-sided die. And it looks like this. In one line notation, it would look like this. So you can see my 3 copies, and you can see the values that I insert in between the copies of the original dice. So let's look at that again. So that's the one line notation. And in fact, if I write that out, remember that that one line notation is just telling me where to place the values on the dice. And if I use consecutive values, which is what I've done here, this is what you get. So now I'm using consecutive values instead of that 100 and something, 200 and something, 300 and something. And I get this set of 4 permutation fair dice. So there you go. It all works. That is permutation fair. And because each order is equally likely in the complete set, that will work for subsets as well. That's all automatic. So all subsets are going to be equally likely too. There's no work to do there. So that is our set of 4 permutation fair dice. So I'm now going to show you how to do this in general. That was just a working example. So in general, you would have a set of n permutation fair dice, x1 to xn. That's what we're starting with. Then we create an expanded set by making r copies. And that, again, is a choice you can make. So you make an expanded set with r copies. You then create an additional dice, a new die, by inserting values in between those copies. And then you create your permutation fair die. And the equations that you're solving, if I put them in compact form, this might look dizzying, but in compact form, that calculation I did earlier looks like this. That's the calculation, that's the equations you're solving. There you go. And that is for, I don't know if you can see L in that equation, L from 0 to n. So I'm saying there are n plus 1 equations to solve, simultaneous equations to solve, and if you solve them, you get your values of ki. That's me just putting that into general terms. However, I can make this neater in one way. There is one way to make this neater, because this whole argument that I've just done works for subsets of dice as well. So my original set was x1, x2, up to xn, and I can take subsets of that and apply the same mathematics. And in fact, if I take n to equal L, now in that previous equation, L was 0, 1, 2, 3, up to n. So what I'm saying is, I'm now going to take subsets that are subsets of 0, subsets of 1, subsets of 2, subsets of 3. You do those same calculations, the equations just get neater. That's all I'm trying to say. The equations look like this now. So a much neater set of equations. In fact, that little argument that I've just made there is actually equivalent to calling, by looking for go first fair dice. And that's what Eric Harshbarger did. So originally he said, if these dice are goes first fair, these are the equations I find. And that's what you would get. If you assume that they're permutation fair first, then you get the slightly nastier set of equations, but you get the same solutions. They are equivalent. So those are a nicer, little neater set of equations to solve. So you've got these equations to solve. If you do it, I'm going to create a little table of solutions. So this is a table of solutions. On the left-hand side is the number of dice that I've got, 1 to 6. That's what I start with. Along the top, I've got how many copies I'm going to make for my expanded set. And I've just filled that in with 1 to 6. Got equations, solve the equations. Here is a table of solutions. These are the answers you get. These solutions are telling you how many values to insert to make your new die, your additional new die. I'll show you an example, because what's really nice about this table is you can start from scratch. You can start with a trivial one-sided die, A, which has one side. Okay, we'll start with the trivial die A. Now to create 2 dice, what I do is I go to my table, I look at, okay, I'm starting with 1 die, and I'm going to make 1 copy of it. So there it is. And this tells me to insert 1 value and another 1 value in the gap. So that's going to be either side. It looks like this. This is die B. So it looks like BAB. Now, what about making a new die, another one? What I'm going to do is look at my table. I've got 2 dice. I'm going to make 2 copies of it. And so it looks like this. And now in those gaps, I can insert 1 value, 4 values, 1 value. Looks like this. That's die C. Then I take those 3 dice. I'm going to make 2 copies of that. So it looks like this. And my table tells me to insert 1 value, 4 values, 1 value. You get die D, and so on. Okay, and for the 5th die, you could take that set and you would make 4 copies according to this table. And you make 4 copies of that, and you would make the E die. However, I'm not going to do that because there is a better solution. Because instead of using that option, I would prefer to make 6 copies of this set. If I make 6 copies and insert my values according to that, I get smaller dice. In total, the number of faces would be smaller. So that's actually my preferred option. And if I do that, I create a set of 5 dice, which looks like a 24-sided, a 48-sided, 72-sided, 36-sided, and then 20-sided, which is that last one that you've made. And that's it, a set of 5 permutation fair dice. However, again, that's not our favorite set, because the 72-sided die, it's a bit big and it's a bit awkward to make. We wanted to make these for real. So we actually have a preferred solution, which is this, starting with this set of 4. This is a set of 4 in that 1-line notation. And I'm going to point out that set of 4 was not found by induction. That set of 4 was found by computer search. So that was a set of 4 found by computer search, but then we create the 5th die by induction. So we take that set, make 6 copies of it, insert those values, and hey, we get our final solution, which is this. And here they are for real. So we printed these out as well. And so this set of dice is 36-sided. It is 48-sided, 48-sided again, 54-sided, and 20-sided. But only that last one was actually made by induction. So that was found in 2018. And I'll just say maybe one other thing about this. They are weird sizes though. So what about if I was interested in making them the same size? Because that's kind of nicer. Well, I think it is. This is the best solution we have in this method. So if we want dice the same size, then we do have a solution. There is a set of 4 18-sided dice, and that's what it looks like in notation. So this is a set of 4 18-sided dice. If you then make 10 copies of that, you would create 180-sided dice. Then you would insert values to make a 5th dice, which would have 36 sides. Take that, multiply it by 5, make 5 copies of it, and then you finally create a set of 5 180-sided dice. But that is much larger than my solution, which was the 60-sided dice. And these are the pros and cons. So we got these 2 answers. With the binary set, like this, we have these necessary conditions that eliminate, and there's a computer search, but you will make dice the same size because they're designed to. But you then have to check for place fairness, permutation fairness. With the inductive set, it's a direct construction, and that is nice. But you do get weird sizes. That might bother you, that might not bother you. They will be permutation fair, but the sizes get really large. So we could use that method to make 6-player games and 7-player games, but the sizes of the dice get very large indeed. Yeah, neither of these constructions are comprehensive. We haven't found all the possible sets. Like I said before, we think maybe there's 30-sided dice out there, and we haven't found them. So maybe smaller solutions exist. I'll end there. I can tell you where to find all the details about this stuff. If you're interested in this stuff, I'll tell you where to look at. There's also some websites that have Go First Fair checkers, which is really nice. If you think you found a set or a solution, there's a website that checks if it's a solution for you. So I can tell you where to find that. Yeah, articles out there exist, and I'll leave it at that for now. So a couple of things that I would like some help on if you're interested in this, and I will leave it at that for now.
Cool, thank you very much. I don't know if doing a round of applause means anything on a video call, but please feel free to do this in front of the camera if you would like to applaud James. I don't know if you can see everyone's faces. So I think there's been a couple of questions that have come in the chat during that last section. So if we take those couple of questions and then we can go to a short break before the second talk. So one of the questions was, is there a way to kind of create permutation fairness using some dice which are place fair by, for instance, starting with a set of 5 dice, rolling them to determine who goes first, then rolling 4 dice to determine who goes second, and then rolling 3 dice? Would that give you permutation fairness as a consequence of doing it that way?
Okay, well, I'll have to think about that. So I can't tell you that off the top of my head. That is something to think about, yeah.
I mean, you want your large unwieldy set of ridiculous dice to be simple, right? You don't want them to require any thinking. Another question, how important is it for something to be permutation fair?
I mean, it's just nice symmetry, and that's all it is. This is a really pure maths thing. I didn't say there was any applications to it or anything like that. Just nicer symmetry. It's a stronger definition of fairness, because if it's permutation fair, it's automatically place fair. So that is nice.
Yeah, I can see how people would, mathematicians would definitely appreciate it. I guess if you're not a mathematician, then you look at this problem and go, okay, well, if we roll some regular dice and see who gets the highest number, it may be that we all get the same number. We can just roll again. And a mathematician will be like, but technically that could go on forever. And they're like, we've already finished. What are you talking about?
Yeah, exactly. I can see some use for having a set where each order is equally likely. If I could think of a practical application, I haven't thought of a practical application, but maybe if there was one, maybe it would be important that each order is equally likely. So there's something that you've set up and you want to find all the orders. And if they weren't equally likely, maybe there's something you're wearing out, right? Maybe there's something you're manufacturing, right? And then you want to swap them around. And if all the orders aren't equally likely, something gets worn out. I mean, I don't know, because I've just made that up off the top of my head.
Well, they do a lot of stuff with things like design of medical trials and things where they use like Latin squares to determine who gets what, so that they know that they've tried every combination and things like that. So it's maybe, there are maybe some nice applications. Okay, so I think there's sort of more of a comment than a question in the chat, so I won't necessarily read that one out, but you're welcome to have a look, James, and respond in the chat. I think it's probably a good point to have a break, so I'll hand over to David. I don't know if you want to determine how long the break will be and so on.
Okay, did we have a time in the schedule that we agreed on for?
It's variously been 5 or 10 minutes. Time to get a cup of tea, I guess.
Yeah, so, you know what, let's say 10 minutes, make sure everyone can get a hot drink and whatever else. So we will pick up the next talk promptly at 20 past the hour. And just a moment to say thank you to James again for the talk. Thank you.